So far we've dealt with moose, cats, and now we have lemurs. The rate of change of the number of lemurs in captivity, L of t, is modeled by a logistic differential equation. They didn't give us the equation. Oh no, we'll be all right. The rate of change of the population is 2 lemurs per week when there are 430 lemurs in captivity. Stop right there, write some stuff down. The rate of change of the population, dl dt, we're using L because, well, they said so, and lemurs, is 2 when the number of lemurs is 430. That's just good to know. We might use that in just a minute. And the rate of change is a maximum when there are 310 lemurs. What can we do with that information? Okay, the rate of change is a maximum. The rate of change of a logistic equation is the most. Notice steepest slope on this entire graph happens right there at that point. It happens at half of the carrying capacity. So this little guy right here is 1/2 of the carrying capacity, which I normally call L. So let's not get thrown off. I might be like, oh, L is my carrying capacity. Yeah, I hear you. L is carrying capacity, but now right now, L is the number of lemurs. So I'm just going to write it out in words. So carrying capacity. There we go. That doesn't look like I wrote capacity, but I wrote capacity. That is my maximum carrying capacity. Well, that's half of it. So my carrying capacity, I'm just going to write this over here. So my carrying capacity, again, normally known as L, can't do that in this case because we're using L in other contexts, is equal to 2 times that, which would be 620. Okay, good to know. So what I'm going to do is switch colors for contrast and write the differential equation that goes along with this. And I'm going to use this right here as a guide. So dy dt equals k times y times L minus y. Again, L is carrying capacity in this context. L is lemurs in this context. Why do they do that? To make you angry. Why don't lemurs start with a different letter? Don't know. So dt equals k times the number of lemurs times, okay, we got to get creative with carrying capacity. I'm going to call it C. There we go. We'll do that. C minus L. And I'm basically following this format right here. So carrying capacity, I'll call that C. I'm going to call carrying capacity C right here. And so C is my carrying capacity. Let's plug some numbers in and we'll figure out what we don't know. We still haven't even really started the question. We're actually doing number 10 without even reading the rest of them. Oh no, that's okay. We'll be all right. So dl dt, oh, we know that's 2. Do we know K? No. Do we know L? Yep, it's 430 at a specific moment. And 620 here, minus 430. And we're going to solve this thing for K. And when we do, we will have, let's see. 2 equals K times a bunch of stuff. So 430 times 620 minus 430. Key got stuck there. Didn't want me to subtract. And I have 81,700. This is going to be crazy, y'all. K is equal to 2 over 81,700. Let's reduce because we should. 2 over 81,700 gets reduced. That's not going to work too well. It's not. 81,700 divided by 2 will give me 40,850. So K is 1 over 40,850. That is equal to K. So let's move on. Find the limit as t approaches infinity of dl dt. Whoa, what? Okay, as time continues, at what rate did the number of lemurs change? 0. We are leveling off. So we didn't have to do any of this work for number 8. So 0. What is the carrying capacity of lemurs? We already found it, 620. Number 10, write the differential equation. Oh, good thing we did all this work. So the rate of change of lemurs is, and this is differential equation, so we need the slope. It is K times the population of lemurs, and then the carrying capacity minus the number of lemurs. And again, I'm using this general structure to guide what I'm doing. So we could plug in lemurs and get the rate of change of lemurs.